My name is Cooper Barth, and this is my end of quarter update for spring quarter 2020. So, what if a system could leverage community members' existing routines to get them to help others? For example, imagine that Ryan, a Northwestern college student, is sick and needs cough drops for his sore throat, but he's stuck in class all day. As Stella is walking back to campus, she passes by a local drugstore and gets a notification on her phone about Ryan's problem. Stella is heading back to her dorm, which is nearby Ryan's location, so she decides to bring him cough drops because it's convenient for her to do so. Ryan gets the cough drops, and Stella is happy that she was able to help somebody without going out of her way. So this is an example of a common interaction in what we call an on-the-go tasking system. These systems are built around community members opportunistically completing tasks for others in a low-effort manner. People that help in these systems, called helpers, are volunteers. Whenever they're notified about a requester's task, they are free to choose if and when they want to complete it. This makes these systems opportunistic. Because of this, in on-the-go systems, somebody could act as a requester at one point and then as a helper at a later time. Although on-the-go tasking can be situated in any setting where a community of volunteers complete tasks for each other, for the rest of this presentation, I am going to be talking about it within the context of a volunteer-based food delivery application, akin to Postmates or Uber Eats. So there are a few different user classes at stake in these systems. The first is requesters. So obviously the main goal of requesters is to get their tasks completed. They can also have any number of other goals, and these often change on a per-request basis. For example, for one request, Ryan could really need to get his coffee soon, or else he doesn't want it. For another, he could be studying with friends in the library and doesn't want to walk very far to meet his helper. So the second user class is helpers. So their primary motivation for participating in these systems is convenient altruism. So they want to say, sure, I'll help out this person as long as it's convenient for me. As a result, their primary goal is to participate without their schedules and routines being significantly disrupted. Since on-the-go systems are based on community members both placing and fulfilling requests, as I mentioned earlier, somebody who acts as a requester at one time could act as a helper later. This also creates a feeling of positive reciprocity within the community, where helpers can think, I've been helped by others in the past through the system, maybe I'll accept this request in order to do my part. However, in order for these feelings of reciprocity and altruism to drive the system, the goals of users as both requesters and helpers must be met. So a major problem for requesters in on-the-go systems is the uncertainty present in leaving the fulfillment of their orders to volunteers. So when you place an order with Uber Eats or Postmates, you never think, I wonder when and where I'll get this order, much less, am I going to get this at all? This information is presented to you up front. The system knows these details for certain because it can just tell a helper to accept the order. However, in on-the-go systems, if there's nobody passing by where you want food or nearby where you are, you might not be able to get what you want quickly or at all. Requesters in on-the-go systems are essentially in a black box, as details about task completion are a total unknown at the time of order placement. Due to this uncertainty, they will often forego the use of these systems, instead opting to use other services or just complete the tasks themselves. We could just notify more people in the hopes that somebody picks up, but over-notifying helpers causes massive disruption and can lead to notification blindness, where users stop paying attention to notifications just because they receive too many and they just receive notifications about requests all the time. So a vital question to be examined is, how can we help requesters reach their goals while still maintaining low levels of community disruption? So in directed systems like Uber Eats and Postmates, requesters know exactly when and where they're getting their stuff. Helpers, in this case something like delivery drivers, perform tasks on demand and are directed to deviate from their daily routines in order to complete orders. However, in volunteer-based systems, like on the go, we can't tell volunteers to fulfill orders immediately because it might interrupt their plans or activities. In a purely volunteer-based system, instead of directing helpers to complete tasks, we simply notify anybody that passes by an open request pickup location and wait for somebody to accept. There are some existing systems that expand on volunteer-based tasking, such as supplyman or hit or wait, and these systems introduce scaffolds for helpers rather than requesters. These systems work to minimize this disruption for helpers, which is the amount of notifications that they receive, by managing who is notified about which request at appropriate times. The systems prioritize that disruption and effort for helpers are low so that they choose to participate, while still pinging enough people to get requests completed eventually. Although these approaches take community and system level goals into account, they don't provide enough support for individual requesters to see their goals explicitly met and help them understand the outcomes of their requests like directed systems do. So the first outcome that we are trying to reach is to help requesters understand how they should interact with on-the-go systems in order to reach their goals. While an absolute assurance of task details is impossible, requesters want to know how they can have the best chance to get what they want. Meeting point placement is vital to getting requests completed in a delivery setting, as helpers are generally more likely to pick up requests that are close to their paths. If I want my order around 3:30, I need to know where I should choose my meeting point in order to have the best chance of that happening. So when I talk about decision-making or requester interaction in the setting of on-the-go delivery, I'm referring specifically to this task of meeting point selection from here on out. So it's hard for requesters to understand how to elicit value from their participation due to this uncertainty. Because helpers pick up tasks whenever it's convenient for them, requesters have no way of knowing the outcome of their requests and the outcomes of their choices. We can show them information about the locations of potential helpers, such as Uber showing drivers in the area, but this doesn't provide requesters with useful information about when, where, or even whether these helpers will accept their request. We can also show requesters predictions about helpers' behavior to help them get a better sense of their options. However, showing all this information creates an information overload that's very hard for requesters to parse. It also makes it difficult for a requester to make decisions when they have different or multiple goals for a request, such as getting their request around a certain time or relatively nearby their location. In order to help requesters understand how best to reach their goals, my first approach uses predictions about individual helper behavior to help requesters explore different choices that align with their goals. Since people's daily routines tend to follow the same schedules, we can compare a potential helper's current activity with their past activity to predict where they'll go next. We can then use this information to present to requesters suggestions for where they can choose a meeting point in order to have the highest likelihood to get what they want. For example, if person A wants their request around 2 p.m., we can let this person know that there's a high chance for their request to be accepted if they place the meeting point near Mud Library, as there are 4 helpers predicted to be there around that time. If they then play around with the filter and move it to around 2:30, they can see that there's an area much closer to them that works better. This allows them to very easily visualize the trade-offs between different options, in this case time and distance, and explore what works for them. By providing requesters with an interface through which they can filter potential meeting points by things they care about, like time of delivery and distance to potential helpers, we help them understand how to tune the interface to find options that work for them. Although this approach does help requesters understand how to make choices that are predicted to align with their goals, it still doesn't provide any support to make sure that those goals actually happen. If some requester is totally unable to move some moderate or large distance to get their request, and nobody notified about it is passing by their location, they're out of luck, regardless of how much we let them explore this interface. But getting these tasks done sometimes means disrupting potential helpers more by sending more and more notifications, which, as mentioned before, is a no-go. So our second desired outcome is to work towards achieving desirable outcomes for requesters while still maintaining low community disruption. A common approach for deciding how to notify helpers about requests is to notify all potential helpers that pass within a certain radius of a pickup location. With this approach, there's no guarantee that the system can meet the requester's specified constraints. If we notify every requester in, say, a 25-meter radius about a request, there will be many times where the needs of a requester simply can't be fulfilled. If a requester wants something around 2 p.m. and all the helpers that walk within the 25-meter radius will do so at like 3 p.m., or they won't pass anywhere near the requester's location, no amount of prediction and exploration with an interface will help that requester actually get what they want. Additionally, these policies can miss opportunities. The helper on the left here is passing right by the requester's location at the right time, but because the radius of the request is fixed, that person will never be notified about the request. Some more intelligent approaches adopt community-level policies that decide how to notify users about requests based on global supply and demand. For example, around lunchtime, it could automatically increase the radius of notification around pickup locations in order to capture more helpers, sacrificing some disruption in the process. Approaches like these that make community-level decisions as to how to notify helpers fail to take into account the needs of individual requesters, instead just balancing overall likely task acceptance with helper disruption when making policy choices. This approach also fails to capture secondary goals of these individuals, such as speed of delivery and distance traveled. For example, if requester A cared more about getting the request quickly than requester B, the system would have no way of knowing and would establish the same notification policy for both, potentially fulfilling person B's request far earlier than person A's by chance. My second approach in order to solve this is to modify how potential helpers are notified about requests on a task-by-task basis in order to maximize predicted community and system value while meeting each requester's needs. By looking at what each individual requester needs, we can tailor the notification policy used in each individual request to maximize the value the requester gets given their specified goals. This may involve growing a notification radius to notify users who are better suited to fulfill some specific set of goals, or it may involve shrinking the radius to remove extraneous users whose paths were originally contained in the notification radius but probably wouldn't accept the request anyway. For example, requester A specifies that they don't want to go very far to meet their helper. So in this scenario, we can change the notification policy of the request to only encapsulate potential helpers that are predicted to pass by very close to the requester. In another example, if a requester wants their order at 2 o'clock, we could expand the radius a little bit to notify a helper that we see can pick up around 2 o'clock, like in the previous example. Not only does this small change help the requester, notifying this new helper may actually decrease community disruption, as the request is removed from the notification pool once it's accepted. More importantly, under a dynamic notification policy, we can make these two changes in these examples independently, shrinking the coverage for one request and expanding it in the other. If it were lunchtime and we were to expand the request for the radius for both, like in previous systems, we would be causing unnecessary disruption for request A. On the contrary, if we were to decrease the radius at the community level, the opportunity found for request B would be lost. So the way that we're doing this is by introducing a notification policy manager that for each request looks at the goals the requester specified during exploration and maximizes a value function that's weighted by their preferences. This value function uses predicted change of task acceptance, community disruption, and fulfillment of requesters' goals to determine how good a notification policy is for a given request. The requester puts in what they want, and the system figures out what the best notification policy to use is in order to help that specific requester. Since community disruption is also part of the value function, we don't lose any of the scaffolds for helpers that are in place for other approaches. System designers can also tune the weights of community disruption or any of the other factors in the model in order to prioritize different helper and requester goals, depending on what the system needs at the time. So, in conclusion, on-the-go system designers want to maintain low community disruption while still working towards desirable outcomes for requesters. However, uncertainty in helpers' availabilities make it hard for requesters to understand the potential outcomes of their requests and thus disincentivize them from using these systems. So we help requesters understand how to make decisions to help achieve their goals and introduce systems that intelligently tune how helpers are notified about individual requests in order to help fulfill these goals. Thank you very much.